And you said the radius was a
3.
smaller. It was smaller than that radius, right? It was just a slice from that sphere inside of it. And what's the center? Let's write the center in terms of x, y, and z. Because we were still three-dimensional, right?
2, negative
2,
3 and 0.
negative 3, and what's this number?
0.
There you go. That's the center. That was a good description. By the way, that's why problems like that, you might be like, when you ask for the intersection, am I going to know to do a description and write the equation? So I usually write that question like in a multiple choice. Anyway. Okay, super. Now when that's 12.1, that's the introduction to the three-dimensional coordinate system. There's some other things with sketches and things like that, but the sketches are going to come involved when we get into section 12.6. I'll show it to you, but I do want to point out, don't get too concerned with this problem. It's the last one I'll do from 12.1 before we do 12.2. You can say to yourself, he said this will become more important in section 12.6. They threw a problem in the book. I just didn't want someone to go home tonight and go, all right, I'm doing every problem in this section, but this one bugged me. Here it is. They wanted you to describe this.
What page is this in, Professor?
This is on page 791.
7.
They just want you to put in words what the heck this is. So I just want to talk about it. I'll give you a heads up. That's a sphere equation, right? So this is not a sphere. That's the first thing. Page 791, and when the problem number was number 33. They just want a description of this. Okay. Now, again, don't get too concerned with this problem right now. This will become much more important in this section. So I'll put important. But sometimes it's cool to just think about this right now. Here we are in 12.1, it'll become important when we get to 12.6. All right, let's really think about it. But I think we have enough information to go with to really get a sense of this, okay? That's not a sphere, is it? Because the sphere would have all three of these, true? Now I'm thinking, well, just two variables. Earlier I had something like this. I wrote a circle on the board. So maybe that's a circle. Well, they're asking you to describe this in three-dimensional space. What would this represent? And three-dimensional space, sometimes they just call it three space. Sometimes they just write this. These are the different notations to let you know you're in three-dimensional space. So then, if this is three-dimensional space, everyone, this isn't a circle anymore. Yes, you put an equal sign there, just on one plane, that's a circle. But in three-dimensional space, for given this equation, we got to still consider that other letter. What's the other letter?
Y.
So when you don't see y in this equation, I want to point out, it doesn't mean y is 0. It means y is anything. Y can take on a 0, a -1, a -2, a -12, a -1 million. A positive million in this relationship. X and z must always have this relationship. Right? Like the circle kind of thing? But y gets to be what? Anything. So can we kind of get an idea what the heck's going on with this thing? Do you know?
I'm going to take a guess. Would it be like an infinitely long cylinder?
Brilliant. Yeah, you couldn't have said that better. What's your name again?
Brad.
Brad, you nailed it. And when he calls it an infinitely long cylinder. He's talking about a circular cylinder. If you want to even put the word circular, so you didn't think it was like some kind of like elliptical cylinder. You're talking about like a, I'm looking for the trash can isn't circular, right? So now I'm looking around the room. This is the closest, huh? Although it's starting extending, that's the closest to a circular cylinder in the room. That's close without the top part, right? Anywhere else in the room? Usually we can find things. Right? Your cup right there is the closest to the circular cylinder, right? It was the circle we were talking about that, but y got to be what? Anything. So if you wanted a rough sketch, wasn't this the y-axis? This was the z and this was the xz plane. I can make a radius. What was the radius? Radius of 3. Just like, yeah, you can distort it a little bit because it's three-dimensional space. He says, but now y gets to be anything. So this will always occur what? All the way down here. You can make another trace. we want to make a schedule. And this keeps going, doesn't it? So if you want to do the negative y-axis, this just keeps what? Going forever. Infinitely long. Brad, way to go. That's a cylinder. So we're talking about a surface here. All right, very good. One more thing. If this was an equal sign, we're just talking about the surface. Just this part. Just this part, the surface. Well, what was here? And I just heard the word. Less than or equal to, she said the word solid. So I would have to take this cylinder and fill what? All the points inside it. So we'll add some warning, Brad, to your description. Infinitely long cylinder, but all the set of all points inside that infinitely long cylinder. And on the surface. The set of all points inside and on the surface of that infinitely long cylinder. Boy, that's your description. And that's your image. If you want to shade it all in, you can, because it had that less than or equal to. And you got it. That's great, you know that, everyone. This is when it becomes important, when they just want to make sure we're comfortable with all the surfaces. You got cylinders, but we also have a thing called a quadrant. That's a quadrant surface. We have all these other quadrant surfaces that can go. All right, let's go to 12.2. 12.2 is on vectors. Man, there's so many people in the room going into engineering. People can already have experience with vectors from your physics courses, etc. But still, there's a student that could be sitting in this room right now. They've never heard of a vector. They don't know what it is, so we got to define it. You know, a vector. What is it? Well, we can call it a quantity that has two things. It must have a magnitude and a direction. You got it. So that's the definition of vector. It's a quantity. It must have a magnitude. It must also have a direction. I mean, some examples, I guess we could say like a velocity, displacement, a force. Will that work? So everyone, this is what 12.2 is all on, just vectors. And if you have really good experiences, great. Here's a vector when I'll start from the origin and I went over 1 this way and I went up 2 this way. Will that work? We put an arrow, don't we? We draw an arrow to draw the direction of the vector. There's a couple ways. I can call this vector A. I can put a symbol over it like a little hat there, and that's vector A. And then I can write vector A, and I can write this in a couple notations. One is, this is component notation. And that's the x component, that's the y component. Remember, I want to teach us, so like someone never had vectors before. That's one type of notation I can use for vectors. This is the one I use mostly in our course, because I find it easier. If I use the standard basis for it, that's where I put a 1, I put the letter I, right? I put a little vector of the I, plus, what's the next letter? J. That's standard basis format. Of course you can write like that on every problem you want. I just find that this took less writing, didn't it? So you'll notice, you know, in my lectures I'm used to usually writing this, but if I see problems in a book where the problem's presented that way, I'll do it as well. The weirdest thing is when you see a vector giving you like this. This throws students off sometimes. They go, all right, vector v equals k. And they'll go, what? And they put the letters in boldface print. Can you put that in component form like this? I just think you'll find it easier. So a student will be like, hey, I left that problem blank on the test. I go, what? They go, that k thing was bugging me. I go, oh, that was just the vector. Tell me these 3 components. What's that's a 0. That's a 0. Didn't have an I, didn't have a J, and what number's here? And the minute I say that to them, they're like, oh, you're kidding. Are you kidding? I would have got the problem right if I knew it was like that. So just to be comfortable between the 2 notations.
I was looking at some book. Somewhere they use the hat because that's on like a unit vector. I, J, K are each unit vector. So can you use the hat also like a?
You can. I have a colleague. He likes to write everything like a matrix, but he does it this way. So see this number here? He'd write that thing like a matrix this way. That's another way to be written.
No, I'm saying instead of I on top of IJ, can you use the hat? Like
yes, you can. That's another notation you can use. Absolutely. He says I put little hats rather than these little what? The nose things. You surely can. Very good. All right, so now we know what these vectors are. You just brought up a term. We should make a formula for this. This is important for a course. Unit vectors are important in calculus 3. Unit means what length?
One.
The length of one. So you hear the word unit vector. A unit is a length of one. So we need to create a formula for our class to find unit vectors. I'll use the vector I had before. What was it? 2. And when here's my question, can you find a unit vector that has the same direction as 1, 2? So we need to create a math formula for unit vectors. We're going to do them so much in our Calc 3 course. All right. First of all, let's talk about that length. We got to start there, right? 1, 2 means it went 1 this way, 2 this way. If you want to watch that PowerPoint I was talking about, I called it the introduction to the three-dimensional space, and I just titled the PowerPoint the Pythagorean theorem. Because everything comes from the Pythagorean theorem. This comes from the Pythagorean theorem. If I want to find the length of that vector, then I take the x component, I square it, I add the y component, I square it. A squared plus b squared equals what? C squared, right? Pythagorean theorem. So the length of this vector, let's call this vector A again. A equals, what is the magnitude of A? So we put bars around it. The notation for length, magnitude. It will be the length of that vector. We put bars around it, and we put the actual length. I'll put in parentheses magnitude of the vector. How long is it? Square root of 5. And you did this by which theorem? Pythagorean theorem. I know. The Pythagorean theorem, everyone, in my little PowerPoint, I didn't know if you knew this, but you'll notice it's like Pythagoras really invent this theorem. You're really like, and when they still have no written documentation from Pythagoras. So we don't even have like written proof of that, like he really was a mathematician. But there were Pythagoreans, they liked to do math. And so the evidence that we had, they named it after him. But now there's evidence from like Mesopotamia, China, Babylonians, who knew about this theorem well before Pythagoras' time. So, but, once they name it, it gets named. So I just want to point that out. It's interesting. When it's named the Pythagorean theorem, but other cultures knew about this in a right triangle with that relationship too. So, all right, that's the length of A1, but we need a unit vector that has the same length as that. What can I do?
Don't you just multiply it by 1 over the square?
That'll do. So you just created the formula for unit vectors. You said, if it's in the direction of a vector A, you said just multiply 1 over the magnitude of that exact vector. There's the math formula. You can think of this, multiply to it, or if you want to write it like this. Take your vector and divide the magnitude from it. You'll always get a vector that has a length of 1. Because you can multiply any scalar multiple to a vector. Cool. This was a little too long, wasn't it? She goes, okay, divide that out from it. So here's my answer. Now, can I leave my answer like that? Sure. Hey, if you want to use the letter U for unit vector, U. U for unit, there it is. Can I distribute it? Of course. And then you can do this. 1 over rad 5, comma, 2 over rad 5. Do you want to rationalize the denominators? You don't have to. I'll repeat that. You do not have to. You do not have to rationalize the denominators. I know some of you like to. Rad 5 over 5 and 2 rad 5 over 5, right? That's just as nice. And you can leave your answer like this too. That means we can multiply any scalar multiple to any vector. It still goes in the same direction, doesn't it? Hey, we should talk about the triangle law. We got the unit vector formula, right? Let me just put it here. Unit vector in direction of vector A. Vector A divided by the what? Or write it the other way, whatever way, or I just wanna leave, every time I get a formula, I might as well leave it up there. Can we talk about the triangle law of vectors? Alright, here's vector A. Stops there. And then vector B starts here, stops there. What can I call, going from here to here, here to here? What can I call this? And I'm gonna put an arrow. Does anybody know?
A plus B.
A plus B. This is by the triangle law of vector addition. This would be vector A plus B. Going in. Now let's draw it another way. Sometimes the triangle looks weird, right? Something went over here. Then it went down here. You can think of it as a ship sailing. This was vector A, and this was vector B. Where's A plus B in here?
All the way like this.
You got it. Look, I started here, went to here. Started here, went to here. It's like, where did I originally start and where did I originally end? So I started here, and I ended what? I'm gonna put my arrow like that, and I can call this what?
This is the resultant vector in physics, right?
That's right. Hey, what's this? A, B, C, D. What can I call? I'll put it in yellow. Start here, stop there. What can I call?
A plus B plus C plus D.
You got it? And you're just extending the triangle law. You could have kept doing this, but that's what it is. Look. A to B, B to C, C to D. This would be A plus B plus C plus D. And some of you are really familiar with this. You've seen vectors before, but I want to make sure everyone's comfortable with this triangle law in terms of which way that's written and stuff. I'm just going to leave vector